In this example, we're going to talk about will a precipitate form and involving the KSP. So remember that KSP expression that we had talked about? It depends upon the concentration of the ions. So I think just recently, we did something like this, KSP, and the KSP expression is dependent upon the concentration of the ions. So questions involving this expression right here, okay, from a given phase equilibrium equation, that's the KSP. So the other thing we talked about were the solubility rules, which, there's the KSP values. Solubility rules, I thought I had them, oh yeah, here they are. Nope. Solubility rules, where'd they go? Here they are. Okay. All messed up from my lesson the other day. But you remember going through these rules, you should have a copy of those rules in front of you. And these are the rules that we're going to talk about. So if we're given a solution, right, of different substances that are dissolved, we can predict whether or not A, they should form a precipitate, and B, we can decide if one is actually going to form based on the concentration of the ions. Okay, so two things, and that's what this question asks us right here. It says, when you're given silver nitrate solution and it's added to potassium iodide solution, the first question is, what possible precipitate may form based on the solubility rules? And the second part of the question is, will that precipitate actually form? Okay, so this is the kind of question that we need to be able to answer. And so what we're going to do is we're going to look at the solubility rules to determine what possible precipitate may form. But I guess even before that, what we should look at is what ions do we have involved in this solution. So we have 10 milliliters of 0.1 molar AgNO3, right? And so what we're going to have is we're going to have this AgNO3. And I know that you guys have this in front of you, the worked out solution as well. You're going to want to maybe take some notes here as well, because I will put things in here that you don't have in front of you. I'll fill in steps. I'll add little things. So please compare very closely what I'm doing up on the board with that kind of worked out solution you have for this question, okay? Because you may need to add. I don't want you to lose focus. I don't want you to miss anything either, because they may skip some steps there. But anyways, AgNO3, and that's going to break down to Ag ion, right? And that's a 1 plus NO3, 1 minus ion. Okay? So the first thing to understand is we have Ag plus and NO3 minus in solution. Those are going to be in solution. Now, is this going to dissolve? We should even back up even further. Is this going to dissolve? Well, it's a nitrate. So if you look back to your rules, nitrates generally are pretty soluble, right? So where does it mention nitrates? Right here. All common acetates and nitrates soluble. So there you go. We know that that's going to split up, and we're going to have lots of these ions in solution. We'll find out exactly how much in a bit. But the other thing we need to look at is Ki, okay, potassium iodide. Now, is potassium iodide fairly soluble? Like, will it dissolve or dissociate pretty easily? This is where you look back to your rules and just kind of, and you have that visual chart there too, but halogens, so an iodide is a group 17 halogen. All binary compounds of group 17 with metals are soluble, except for silver, mercury, and lead. Okay, and this is not F. So, soluble. Okay, according to that rule. Awesome. So this is going to be K plus I minus. All right. So you look at these ions that are going to be in solution, and again, we won't look at the numbers just yet because we want to find out if a precipitate might form. So what possible precipitate may form? And what you do is you look at the different combinations here, and you say, is there a combination that is insoluble? For example, Ag and I, or K and NO3. Is there a combination that is insoluble? So will there be some ions bumping into each other that have a really low KSP that cannot tolerate having a bunch of free ions in solution, but that have to kind of get together to form that solid again? Okay, sulfates and silver. Well, we have silver here, but we don't have any sulfates. So is there any other rule that may pertain to either a silver and an iodine or a potassium and nitrate? Well, I mean, right away, nitrates, right, are pretty soluble, so it's probably not going to be that. We want to focus in on this one. AgI. Is that fairly soluble or insoluble? So we go back to our rules, or you look at your visual chart there, and what do you see? Group 17, that's the I, are fairly soluble except with, oh, what's this right here? So they are soluble except group 17 elements and silver. So is that what we have? Here's a group 17 element, and here is silver. So guess what? This is fairly insoluble. Another thing sorry, go ahead. No. Okay, so if there's just one that's insoluble, no, it doesn't make the whole thing insoluble. What it does is it tells you that, hey, when the Ag ions and the I minus ions, when they bump into each other, they have a very low tolerance for being separate. They want to be together. So chances are, because that compound itself is fairly insoluble, that means it doesn't like to separate, like it doesn't like to be dissociated as free ions. It likes to be a compound, a solid. It likes to get together. You know what I mean? And so you can't keep them apart almost. So if this is fairly insoluble, we would expect a precipitate to form. And that PPT is precipitate. So we would think, hey, this is pretty insoluble. So if I have silver ions in solution and I have iodide ions in solution, chances are there's going to be some precipitate. Okay? Now the K and the NO3 will still be kind of hanging out in solution. They are fine to be separate because that combination of K and NO3 is fairly soluble, right? It's soluble. That means it's easily dissolved. They don't mind being separate. They can run around and bump into each other and not really care. There's a lot of them that can be in solution and stay separate. That's soluble. I was just going to go back here. That was a good question. Thank you for that, by the way. I was just going to go back here to the chart. If you're wondering how this chart factors in, just remember that we can look for the compound on the chart and then look at its number and decide, right? So AG, oh, look at AGI right here. And what is its number? Is that a fairly high number or a fairly low number? It's 10 to the negative 16, so that is very small. Remember, we said about 10 to the negative 4 or so would be the cutoff, right? Between insoluble and soluble. So that is definitely a lot smaller, right? So AGI has a very low KSP, which means that the product of the concentrations of Ag and I, it doesn't have to be a very large product before solid will form. Okay? So any product above this, solid will form. So chances are we're going to have more than that. Now, the next step then is to say, okay, will this precipitate form? That's the next question. Will this form? So what we have to do, and here's AgI, okay, and if it's in phase equilibrium, whatever, doesn't matter what you put there really right now. But we have concentration of Ag plus, let's find out that, plus the concentration of, oh, sorry, not Cl, wrong one, I minus, right? So we have some ions in solution here, and the KSP for that number, which we just saw, was 1.5 times 10 to the negative 16. Okay, so KSP 1.50 times 10 to the negative 16. So this is a 1-to-1 ratio, so the KSP expression, right, for this is going to be simply the concentration of Ag plus times the concentration of I minus. Are you okay with that so far? Okay. So what we're trying to find out, this is what we got to do. We got to find out what is the concentration of silver in this solution. What is the concentration of iodide in this solution? Then we have to multiply those concentrations together and see if it's greater than or less than this number. Okay? And this is going to be now, remember we talked about a trial KSP? And that's exactly what they call it in your notes there that I gave you, trial KSP. Okay? So we need to find out if this trial KSP, is it bigger or less than the published KSP? Okay, so let's do that first. Let's now focus on silver. Okay, how do we figure out how much silver we have? So let's find out how much silver. Let's focus on silver first. Okay, we've got 10 milliliters of a 0.1 mole per liter solution of AgNO3. So AgNO3 is going to dissociate and dissolve in a 1-to-1 ratio. So the concentration that we have here is that's 0.1 molar is going to be the same, the exact same for the silver ion. Does that make sense? Okay, so 1-to-1. Now, we only have 10 milliliters of that. Okay, so remember, we have for Ag plus 0.1, that's 0.1 moles in 1,000 milliliters. Because that's what molar means. Moles per liter, right? Yes, you remember that? So that's 0.1 moles in 1,000 milliliters. Well, we only have 10 milliliters, right? We have 10 milliliters. So guess what? We basically have to divide by 100, right? So 0.1, and you can say, I don't know how you like to do this, 0.1 over 1,000 is x over 10, right? Simple proportion to find out. The other thing you could do is, I think I might have mentioned this last year, concentration times volume of the first sort of solution is concentration times volume of the second thing. So if we have 0.1 molar, right, or 0.1 molar in 10 milliliters and C1V1, C2V2. Can you, let me just think if you can use this. Well, we'll have to change that to liters first of all. So, I don't know if you're going to want to use this one maybe. 0.01 liters. Okay, so how many moles is that? Concentration times volume is what? 0.001. 0, okay, and that's going to be moles. Okay, that's going to be moles. Now the V2 is going to come with what's the volume of the whole solution. Okay, so you know, and this is where I'd like to just turn you here. How many moles do we have? If you have 0.1 moles in 1 liter, you have 0.001 moles in 10 milliliters. Okay, so concentration times volume. Now the second volume, okay, this V2, we go back to V2 and you have 10 milliliters of this one and you have 90 milliliters of the other solution. So the V2, the volume 2, is what's the total volume when you add them together? So what's 10 times 90? I'm sorry, 10 plus 90 is 100 milliliters or 0.1 liters. Okay? So now you can solve for C2. And so then we would have C2 times 0.1. And divide by 0.1. C2 then is going to be what? 0.01 molar. That's going to be your concentration of silver ions. Okay? So this right here is pretty important. Okay? The concentration that you're given in the volume that you're given. If you want to find the concentration in the new solution, you have to identify the volume of the new solution. In this case, it was 10 mils of the one and 90 mils of the other was 0.1 liters. Okay? So this is the concentration of Ag+. And we'll do that sort of the same thing again for the iodine, so you get to see this again. But the trial KSP equals, now this is 0.01, okay, molar. Now let's work on the iodine. Okay, it's going to be way down here. Okay, the iodide. So it is, what do we have? We have 90 mils, so there's your V1, and 1 times 10 to the negative 10 molar, that's your concentration 1. So C1V1 equals C2V2. So we fill that in. We said the concentration was 1 times 10 to the negative 10. The volume has to be in liters, of course, so it's, was it 0.09? 90 mils. Equals, we don't know what the second concentration is going to be, but with the new volume, we know that's 0.1 liters, 100 milliliters. And so you do this multiplication, divide by 0.1, the C2, so that's the concentration of iodide, should end up to be 9 times 10 to the negative 11. That makes sense? I think that does. Well, this is 1 times 10 to the negative 10, okay, times 0.09. So this is 9 times 10 to the negative 2. So that's going to be 9 times 10 to the negative 12. You divide by 0.1, and that's actually the same as multiplying by 10. So 9 times 10 to the negative 11. You can just punch it in your calculator. It should make sense. If you want to shut that door, you can. I'm not sure what kind of rock music's coming across the hall there, but it's a bit distracting. Okay. Alright? You guys kind of like it? Okay. Whatever. Okay, so the concentration of iodide now, right? And this is pretty important. This is, for some kids, this is the toughest part, trying to get these concentrations. Because after this, it's really easy. So trying to get the concentrations and pull that from the question, that's the toughest part. So that's why we need to kind of practice this. So 9 times 10 to the negative 11. Okay? So we have quite a bit of silver ion and not very much iodide ion. But the question is this enough to make this KSP in the trial, in this experiment, greater than the published KSP? So that means, is there enough ions to form some kind of precipitate? And so what we do is we just simply multiply this out, and you should get 9 times 10 to the negative 13 when you multiply that out as your trial KSP. Hey, everyone with me there so far? That's the solubility product constant for this experiment, this trial. Now, we compare the two, okay? So I always refer to this as published KSP. That's the one that's given in the book. And that was what? 1.50 times 10 to the negative, was it 16? Okay. And the trial KSP is 9 times 10 to the negative 13. So which one is bigger? The negative 13 number is bigger. So this one is bigger, is a larger number. So that means that we have more ions than is needed. This product is the minimum that's required for a precipitate to form. So we have more ions, a higher concentration than's needed. So yes, your answer here, yes, and you can put an exclamation mark there too, because that's pretty exciting that we figured that out. A precipitate will form. And you can use 2 exclamation marks there. It's very important. Got that? Okay. Now, what is that precipitate going to be? It's going to be silver iodide. All right. Okay. So, looking back here, again, I'm just going to review this real quickly. You have to figure out what ions do you have in solution? B, you have to figure out if there's any, combination of those ions that would make an insoluble compound, and that's your prediction. Say, yep, I think this might form. Then the next step is to find the concentrations of those ions, C1V1, C2V2, and then find a trial KSP and compare it with the published KSP. If it's bigger, a precipitate will form. If this number was smaller, So let's say, guys, this was negative 23. If it's smaller, then no, a precipitate will not form, because there's not enough ions, right, to bump into each other to form that solid again. Get it?